Hello, welcome to the video lecture series on digital image processing. Say here, this is the image G, which is given in the form of a two-dimensional matrix, two-dimensional array of size 6 by 6, and our template is a 3 by 3 matrix, which is given on the right hand side. Okay. Now, if I calculate the CFG for this, so what I have to do is to find out the match location, I have to take the template, shift it at all possible locations in the given image G and find out the cross correlation or the similarity measure at that for that particular shift. So, initially let us put this template at the leftmost corner, and what we do is, because our template is 332, 332, 222, let us let us place the center of the template at the location at which we want to find out the similarity measure. So, because of this, 3 will be placed over here, this particular element will be placed over here, this 2 will go here, this 2 will come here, this 2 will come here, and on the left hand side the other part of the template will be like this 2, 3, 3, 3, 2. So, this will be the position of the template, and at this location we have to find out what is the similarity value. So, for that let us find out what is CFG, the cross correlation between F and G for this particular shift. Now, here if you compute, you find that all these elements of the template are going beyond the image. So, if I assume that the image components are 0 beyond this boundary of the image, then these elements will not take part in the computation of cross correlation. The cross correlation will be computed only considering these 4 elements. And here if you compute, you will find that this CFG will, for this particular position, for this particular shift, will attain a value of 47, because here it is 40 plus 2 plus 2 plus 3. So, this assumes the value of 47. Similarly, if I want to find out the cross correlation at this particular location over here, where the template is placed, the center of the template is placed over here, the other components of the template will come like this. You will find that the cross correlation at this location is given by CFG is equal to 56. So, like this, for all possible shifts within this particular image, I have to find out what is the cross correlation value. And if I complete this particular cross correlation computation, in that case you will find that finally I get a cross correlation matrix which is like this. So, this gives the complete cross correlation matrix when this template is shifted to all possible locations in this given image, and the cross correlation value is computed for all such possible shifts. Now, from this you find that here the maximum cross correlation value is coming at this particular location, which is given by 107. And if I take this 107 to be the similarity, or the cross correlation values to be the similarity measure, that means this is where I get the maximum similarity. And because of this, it gives a false match, that it appears that the template is matching the best in this particular location, as shown by this red rectangle. But that is not the case, because if I just by checking it visually, we can see that the template is best match in this location. So, that is why we said that the cross correlation measure directly cannot be used as a similarity measure. So, over here, as we have said, that we cannot use the cross correlation measure directly as a similarity measure. So, what we have to do is we have to compute the normalized cross correlation value. So, for computation of the normalized cross correlation, we have to compute this particular component, that is g square x plus u y plus v double summation over the region A and square root of that. So, this is the one that we have to compute for all possible shifts in the given image G, and we have to normalize the cross correlation that we compute with the help of this quantity. So, if I compute this, again let us take the same location. If I compute this g square x plus u y plus v summation over the region A, square root of that summation over the region A, then you will find that this particular value will come out to be something like 20.07, because this is nothing but 20 square plus 1 square plus 1 square plus 1 square. Other elements for this shift within this 3 by 3 window is equal to 0. So, this is what we get. I have to take the square root of this. So, if I compute this component, I get the value of 20.07. So, this is how, if I compute this quantity, that is g square x plus u y plus v over the region A, square root of this and summation over the region A for all possible u and v, that is for all possible shifts, then finally, this normalization component that I get is given by this particular matrix. So, this cross correlation normalization coefficient have been computed for all possible values of u and v. And then what we have to do is, we have to normalize the cross correlation with these normalization factors. So, if I do that normalization, this is my original cross correlation coefficient matrix that I have computed earlier, and by using the normalization, what I get is the normalized cross correlation coefficient matrix, which comes like this. And now you find the difference. In the original cross correlation matrix, the maximum was given in this location, which is 107, and in the normalized cross correlation matrix, the maximum is coming at this location, which is 7.48. So, now let us see that using this as the similarity measure, that is normalized cross correlation as the similarity measure, what happens to our matching. So, this is the same matrix, the normalized cross correlation matrix. The maximum 7.48 is coming at this location, and for this maximum, the corresponding matched location of the template within the image is given over here as shown by this red rectangle. So, now you find that this is a perfect matching, where the template is where the similarity measure gives the perfect measure where the template matches exactly. So, that is possible with the normalized cross correlation, but it is not possible using the simple cross correlation. So, the simple cross correlation cannot be used as a similarity measure, but we can use this normalized cross correlation as a similarity measure. Now, coming to the applications of this. So, here we have shown that application over a real image. So, this is an aerial image taken from the satellite, and the smaller image on the left hand side, which is a part of the image which is cut out from this original image, and we are using this as a template. The smaller image we are using as a template. So, this is our template F, which we want to match against this image G. So, we want to find out where in this given image G this template F matches the best. So, for doing that, as we have said earlier, that what you have to do is, we have to place this template F, that is, we have to shift this template F at all possible locations in the given image G, and for all possible such locations, we have to find out what is the normalized cross correlation. And wherever we get the normalized cross correlation to be maximum, that is the location where this template matches the best. So, let us place this template at different locations in the image and find out what is the corresponding similarity measure we are getting. So, this is the template and this is the given image. If I place this template over here, we are calling this as location 1. So, this location is given by this red rectangle. Then the similarity measure that we are getting is a value 431.05. If I place it at location 2, which is over here, the similarity measure or the normalized cross correlation you get is given by 462.17. If I place it at location 3, then at location 3 the similarity measure is 436.94. If I place the template at location 4, the corresponding similarity measure is coming out to be 635.69. If I place it at location 5, the corresponding similarity measure is coming out to be 417.1. If I place it at this location 6, the corresponding similarity measure comes out to be 511.18. So, you see that from these similarity measure values, and if I compute for all possible locations, of course, for all possible locations I cannot show it on the screen. So, if I compute this for all possible locations, then you will find that this similarity measure value is coming out to be maximum, that is 635.69 for this location, which is location 4 in the given image. And exactly this is the location from where this particular template F was cut out. And if you look at this picture after placing this template, you find that there is almost a perfect match. So, for a given image and a given template, if I find out the normalized cross correlation for all possible shifts u and v, then for the shift u and v where you get the normalized cross correlation to be maximum, that is the location where the template matches the best. So, obviously, this is a registration problem where we want to find out where that given template matches the best in a given image. Now, to come to the other applications of this registration, you find that this registration is also applicable for image restoration problem. Earlier we have talked about the image restoration problem where where we have to estimate that what is the degradation model which degrades the image, and by making use of the degradation model we can restore the image by different types of operations like inverse filtering, Wiener filtering, constant least square estimation, and all those different kinds of techniques. Now, here we are talking about a kind of degradation where the degradation is given in the form of a geometric distortion, and that is a distortion which is introduced by the optical system of the camera. So, if you take an image of a very large area, you might have noticed that as you move away from the center of the image, the points try to become closer to each other. So, that is something which leads to a distortion in the image as the point goes away from the center of the image. So, here we have shown one such distortion. So, suppose this is the figure that we want to, of which we want to take the image, but actually the image comes in this particular form. Then this distortion which is introduced in the image, that can be corrected by applying this image registration technique. So, for doing this, what you have to do is we have to register different points in the expected image and the different points in the restored image, in the degraded image or the distorted image. So, if once I can do that kind of registration, so in this case this is a point which corresponds to this particular point. So, if somehow we can register these two. That is, we can find out, we can establish the correspondence between this point and this point. We can establish the correspondence between this point and this point. We can establish the correspondence between this point and this point, and we can establish the correspondence between this point and this point. Then it is possible to estimate the degradation model. So, here you find that for estimating this degradation, we have to go for registration. So, this registration is also very important for restoring a degraded image, or the degradation is introduced by the camera optical system. So, the kind of restoration that can be applied here is something like this. Say, if I have an original point, say x, y in the original image, and this point after distortion is mapped to location, say x prime, y prime. Then what we can do is, we can go for estimation of a polynomial degradation model, in the sense that I estimate that x prime is a polynomial function of x and y. So, I write it in this form, that x prime is equal to, say, some constant k 1 times x plus a constant k 2 times y plus a constant k 3 times x y plus a constant k 4. Similarly, y prime can be written as some constant k 5 times x plus k 6 times y plus k 7 times x y plus, say, k 8. So, from this you find that if we can estimate this constant coefficients k 1 to k 8, then for any given point in the original image, we can estimate what will be the corresponding point in the degraded image. So, for estimation, for computing this k 1 to k 8, this constant coefficients, because there are 8 such unknowns, I have to have 8 such equations, and those equations can be obtained by 4 pairs of corresponding points from the 2 images. So, that is what, if I look at this figure, I have to get 4 such correspondence pairs. So, once I have 4 such correspondence pairs, I can generate 8 equations, and using those 8 equations, I can solve for all those constant coefficients k 1 to k 8. And once I get that, then what I can do is, I can say that I want an original image, an undistorted image, and to a particular point to that undistorted image, I apply that distortion, find out a point in the distorted image, and whatever is the intensity value at that location in the distorted image, I simply copy that in my estimated location in the original image. So, I can find out a restored image from the distorted image. Obviously, while doing this, we will find that there will be some locations where I do not get any information. That is, for a particular location, say p q in the estimated undistorted image, when I apply the distortion, then in the distorted image I do not get any point at that particular location. So, in such cases, we have to go for interpolation techniques to estimate what will be the intensity value at that point location in the distorted image. So, for that, the different interpolation operations that we have discussed earlier can be used. So, this is how this image registration technique is also playing a major role in restoration of distorted images. This image registration technique is also very useful, as I said, in image fusion or combining different images, and for that also we have to go for image registration. Say, for example, here we have shown 2 types of images. One are magnetic resonance images and CT scan images. Now, magnetic images, that gives you a measure of water content, whereas in case of CT images, CT X-ray images, that gives you the brightest region for the bone regions. Okay. So, if I can combine the magnetic resonance image along with the CT X-ray image, the fused image that you get, where you can get both the informations, that is the water content as well as the nature of the bone in the same image. So, naturally the information extraction is much more easier in the fused image. Now, again for doing this, the first operation has to be image registration, because the alignment of the images of the MR images and the CT images, even if they are of the same region, they may not be properly aligned, or they may not be properly scaled, they may not be there may be some distortion in those two different images. So, the first operation we have to do is, we have to go for registration. Using registration, we have to get that what is the transformation that can be applied to properly align the two images. And after that transformation, applying that transformation, when you align the two images, then only they can be fused properly. So, here there are two MR images and there are two CT images, and obviously you find that this MR image and this CT image, though they are of the same region, but they are not properly aligned. Similarly, on the bottom row, this MR image and this CT image, they are not properly aligned. So, first operation we have to do is alignment. So, in this slide, on the left side, what we have got is the result after alignment, and on the right hand side, it is the result after fusion. So, in this fused image, you find that the green regions, this shows you what is the bone structure, and this bone structure has been obtained from the CT image, and the other regions contain the information from MR image. So, this is much more convenient to interpret than taking the MR image and the CT image separately. The other application of this is for image mosaicing. That is, normally the cameras have very narrow field of view. So, using a camera which is having a narrow field of view, you cannot image a very large area. So, what can be done is, you take the images, smaller images of different regions in the scene, and then you try to stitch those smaller images to give you a large field of view image. So, that is what has been shown here. On the top, there are two smaller images. These two images are combined to give a bigger image as shown on the bottom. So, this is a problem which is called image mosaicing, and here again, because these are two images, they may be scaled differently, their orientation may be different. So, firstly we have to go for normalization and alignment, and for this normalization and alignment, again the first operation has to be image registration. This shows another mosaicing example, where this bottom image has been obtained from top 8 images. So, all these top 8 images have been combined properly to give you the bottom image. So, this is the mosaic image that we get. So, with this we complete our discussion on image registration. Thank you.